Welcome to this video from the Institute of Physics. I'm David Farley and I work for the Institute as a physics coach. The video is part of our Domain CPD programme. In this video, produced for teachers working with students aged 16 plus, we will be exploring the superposition and interference of waves using water, light, sound and microwaves as examples. Later in the video, you will meet Mark Edwards, who is also an Institute of Physics coach. Mark will show several experiments which demonstrate these wave effects. These examples start approximately halfway into the video, and if you're already familiar with the theory, you can jump straight to the examples. To get students thinking about the superposition of waves, I always like to start with a real-life scenario. This is an imagined situation and designed to make students think about what would happen when two waves meet. I asked them to imagine being cast adrift in a small boat on a flat, calm sea. They look out and notice a 3-metre high wave peak heading their way from the right. Looking the other way, they see an identical peak at the same distance heading their way from the left. Both wave peaks will reach the boat at the same time. Should they be worried? Students always agree that this is a bad situation, and yes, they would be worried. Suppose now, though, that one of the waves was a peak and one was a trough. Would they be worried now? Students find this situation much harder to work out. Somehow it seems wrong to suggest that two waves which individually would be quite destructive can cancel out and leave their boat undisturbed, and yet this is what happens. To find the displacement of a resultant wave caused by two overlapping waves, simply add the individual displacements. Looking at time A on the diagram, we have 3 units plus 2 units equals 5 units. When waves are adding in this way, it seems logical enough, but it's important to remember the vector nature of displacement. So looking at time A this time, we have 3 units plus -2 units equals 1 unit. There is nothing special about time A. Look at any point along the horizontal axis and you will see how the waves add up. In this animation, watch how the red and blue waves overlap. The yellow represents the combined wave. Its displacement at any point is always equal to the sum of the red and blue displacements. If we change the animation so the red wave is a peak and the blue wave is a trough, notice how the yellow dot at the centre never moves. Our student in their boat needs to make sure that they are at this point. We are now going to look more formally at how we predict what happens when two waves overlap. To do this, we need to introduce certain terms that will help us describe the relationship between two waves at any given point, or between 2 points on the same wave. The first of these terms is phase difference, or sometimes phase angle. Waves follow a repeating pattern. Each point on a wave oscillates up and down, repeating once every period. Phase describes how much out of step one point on a wave is compared to another. Since sinusoidal wave motion is closely related to circular motion, the degree to which 2 points are out of step is expressed in degrees or radians. In this snapshot of two different waves, both ducks reach the peak of their wave together, and as time progresses, the two ducks are always at the same point in their cycle. These two waves are said to be in phase, or that their phase angle is 0 degrees. The same could be said for 2 points on the same wave that were one wavelength apart. Because of the cyclic nature of oscillations, being 360 degrees or 2 pi radians apart would also be the same thing as being in phase. To model this, I get students to move both hands up and down in phase. In this snapshot, we see that one duck is at a peak when the other is in a trough. That puts one duck half a cycle ahead of the other. In this special case, we say that the 2 points are in antiphase with each other. In this case, the phase angle is 180 degrees or pi radians. Again, students can model this by moving their two hands in antiphase. Away from these two special cases, we would need to calculate the phase by first working out what fraction of a cycle the two waves, or 2 points on the same wave, are apart. In this diagram, duck A peaks first, then duck B shortly after. The wavelength is 50 centimetres, so to calculate the phase angle, we do 20 divided by 50, which equals 0.4 of a cycle. The phase angle will therefore be 0.4 times 360 equals 144 degrees, or 0.4 times 2 pi equals 0.8 pi radians. We say wave A leads wave B by 144 degrees or 0.8 pi radians. Modelling this with your hand is much more difficult, but it's still fun to watch your students having a go. To work out how two waves relate to each other at some point in space, we sometimes consider the journey each wave has taken to reach that point. Often one wave has travelled further than the other, and the difference in distance is known as the path difference. Mark will now demonstrate a simple piece of apparatus to help students grasp the concept of path difference.
In this picture, you can see that each wave has travelled the same distance from the retort stand to the point where they're overlapping where my hand is. And here the path difference is 0 meters. If the waves are starting off in phase, it means that they will also be in phase at the point where they're overlapping. If I move my hand upwards a little bit, you can see that the bottom wave has travelled a little bit further than the top wave has at the point where they're overlapping where my hand is. And in fact, I've stopped the video at the point where the bottom wave has travelled half of a wavelength further than the top wave. So if the waves start off in phase, at this point here, where the two waves are overlapping, they're overlapping in antiphase, and a peak from one wave will overlap a trough from the other. If I continue to move my hand upwards, you can see that the path difference increases, and we reach a point where the distance of the wave has travelled from the bottom is one whole wavelength further than the distance the top wave has travelled. And at this point, the waves are overlapping in phase, but that only happens if they start off in phase 2. If I continue moving my hand upwards, we'd reach a point where the two waves are overlapping in phase again, and the path difference is 2 whole wavelengths. So you can see that if the waves start off in phase with each other, they will overlap in phase with each other again, provided that the path difference is a whole number or an integer number of wavelengths.
To predict what will happen at some point in space when our two waves meet, we need the waves to emerge from their source in a predictable way. Clearly, if the phase difference between the waves as they leave their source is continually changing in a random way, we will have no way of predicting what the phase difference will be when they reach our point. Two wave sources are said to be coherent if there is a constant phase difference between them. This means that the two waves must have the same frequency and wavelength. Invariably, the two waves will also be in phase. Laser light has the special property that all the photons in the beam are in phase with each other, so laser light is coherent, which makes it ideal for experiments in this topic. Imagine we have two coherent sources of waves that overlap. If the waves are in phase, superposition tells us that the individual waves add to give us one wave of much higher amplitude than either of the component waves on their own. This is constructive interference. If the waves are in antiphase, then superposition tells us that the waves tend to cancel. If they were the same amplitude, they would cancel to 0. If not, like in the earlier example, a small resultant wave may remain. This is destructive interference. In this next clip, Mark demonstrates constructive and destructive interference with water waves in a ripple tank.
You can easily create two sources of coherent waves by using two small dippers and a ripple tank, as shown in the picture on the left of the screen. The two dippers oscillate up and down in phase, and this produces two sets of circular waves on the surface of the water which overlap each other and form a stationary interference pattern. The stationary interference pattern consists of regions of constructive interference, and I'll show you one by moving my mouse along, and regions of destructive interference. Again, I'll show you by moving my mouse along one of them. Where there is constructive interference, the two waves are overlapping in phase with each other, and this results in a wave with a very large amplitude. In the regions where we have destructive interference, the two sets of circular waves are overlapping in antiphase with each other, and this results in a wave with a very small amplitude or no wave at all. Although this is called a stationary interference pattern, it's important to realise that the waves are actually moving, and you can see them doing so in the video. It's a stationary pattern because the regions where you have constructive interference and destructive interference remain in the same place. And that is because the two sources are coherent. If they were not coherent, the constructive and destructive interference regions would be moving around and you would not get a clear interference pattern. Now David is going to talk through how we create a similar interference pattern using light.
In this classic experiment, we produced two coherent sources of light by passing the laser light through the double slit. At point O, both waves have travelled the same path length and so arrive in phase. Constructive interference results in brightness. This is known as a maximum. To reach point A, however, the light from slit S2 must travel further than light from slit S1. If this path difference is half a wavelength, then the waves arrive in antiphase and destructive interference results in darkness. This is known as a minimum. This repeats as we move along the screen and the waves meet alternately in and out of phase, giving rise to a strike pattern of interference fringes. Consideration of the geometry gives us the relationship for the wavelength in terms of the variables shown on the diagram. Mark will now demonstrate this pattern and make a measurement of the wavelength of laser light.
I obtained this picture of the interference pattern of light by shining a red laser pointer through a pair of double slits onto a screen. The slits were 1/4 of a millimetre apart and the screen was 2 meters in front of the slits. You can also see I placed a ruler on the screen and this enables us to work out the value W. You can see that between the 1 centimetre mark and the 6 centimetre mark, there are 10 fringes. But we need to be careful because W is actually the fringe spacing. There are 9 fringe spacings between these 2 points. So now we're in a position to work out the wavelength of the light. As I said before, the distance between the slits was 1/4 of a millimetre, and we need to be careful to convert this into metres. The distance between the slits and the screen was 2 meters. To work out W, you can see that between the 1 centimetre mark and the 6 centimetre mark, that's 5 centimetres, and there are 9 fringe spacings. So therefore W is 5/9 of a centimetre. And again, we need to be careful to convert that into metres. We can now substitute these into the Young slits formula. And when we do this, we calculate the wavelength of the red light that I used to be 690 nanometres to 2 significant figures.
Interference occurs with all types of wave, including microwaves and longitudinal sound waves. First, Mark will demonstrate how the effect can be observed with sound.
We've just seen how to produce interference patterns using 2 dippers in a ripple tank and by shining laser light through 2 slits. We can also produce an interference pattern of sound. You can do this by connecting up 2 loudspeakers to the same signal generator, and this produces 2 coherent sources. Because the loudspeakers are connected up to the same signal generator, they will be oscillating in phase. You can play a tone through the speakers and ask your students to walk around the room, and they should be able to hear the difference between constructive interference, where the sound is loud, and destructive interference, where the sound is quiet. However, this is quite difficult to hear sometimes because of the multiple reflections of the students' bodies and of the walls of the surroundings. To help with this, you can use a mobile phone and download an app such as Firefox, which turns your phone into a sound meter. By moving the phone around the room, you should be easily able to see different places of constructive and destructive interference. I'm going to play the video in a minute, and the phone will move across in front of the speakers, and you can see it passing through 2 distinct regions of destructive interference. The frequency of sound that you're hearing is about 800 Hertz. The loudspeakers are about 1/2 meter apart, and the phone is about 1 meter in front of the speakers. Another nice demonstration you could do is place the phone in a region of destructive interference and ask the students what would happen if I unplug one of the speakers. The students might think that the sound goes quieter because I'm removing one source of sound. However, the sound will get louder. When I unplug one of the speakers, destructive interference is no longer happening.
Double slit interference with microwaves is much like it is with light, but the longer wavelength requires bigger slits. Here's Mark again.
As we have already shown, with ripples and water, light waves and sound waves, we can also form a stationary interference pattern with microwaves. The two slits ensure we have two coherent sources of waves which spread out and overlap each other to form a stationary interference pattern. The detector moves through regions of constructive and destructive interference, and the intensity of the microwaves can be displayed on a meter as shown. Most school microwave kits enable you to modulate an audio frequency on top of the microwaves, which gives an audible indication of the intensity of the waves, which you can hear when the detector is passing through maximas and minimas as a variation in the loudness of the sound.
We hope you found this video a useful introduction to wave behaviour for post-16 study. Do consider watching the other videos in this series. Thank you for watching.